Thank you, Mehmet, for the introduction, and thank you, Metin, for inviting me here. It's really a pleasure to be here, and this university is really, really fantastic, and yeah, really enjoying the time here. I also have a disclosure to make. I am co-founder and CEO of Atlas Endoscopy, which is a company we created to bring our robotic colonoscopy to patients. So I will talk about that, and so I may be overexcited about what I'm saying, so you take my words with a pinch of salt. Okay, I will start by mentioning this review paper, which I was lucky enough to be involved, about medical robotics in the last decade. So in this work, we analyze several areas of medical robotics and the main progresses that happened in the last decade. And there were very, very exciting milestone achievements, but also something interesting in this paper, and that was mentioned by Metin yesterday, is that there is a big focus in this community about automation. So, of course, as automation has been massively developed in autonomous car and automotive, there is, we are trying to do it similarly in surgical robotics. And so going from no computer assistance, so just minimal computer assistant like the surgical robotic platform that are on the market these days, to full automation of surgical tasks. And so during my talk, I will show some attempt we did at automating procedures, including colonoscopy. Also, my talk is articulated in three sections. And those three sections are about three different technological platforms that I've been working on also along my career. So the first one dates back, so I started working on that in 2008, and is about magnetic colonoscopy. And this is also to show you how long it takes to get from an idea to eventually reach the patients. It's not an easy accomplishment, and it takes time. Then I'll talk about magnetic tentacle, which is the topic of my ERC consolidator grant, which just ended December last year. And then something that we started working more recently, which is about Vine robots. So we have seen some Vine robots in a presentation yesterday. We are trying to do magnetic Vine robots. Okay, let's start from magnetic colonoscopy. So why colonoscopy is important? So colorectal cancer is cancer of the colon, which is the last part of the digestive system. And this cancer is the second in terms of mortality rate in the world. So it's a big killer. But this cancer also, as many other cancers, evolves in 5 to 10 years from a stage which is non-symptomatic to a stage which is symptomatic, and so creating pain, bleeding, and so on. And so if it's detected at the early stage here, it can be removed successfully, and it doesn't come back. So there is a 5-year survival rate, very, very high. If it's detected at a late stage, then surgery, chemotherapy, and radiotherapy are needed, and the mortality rate drops really massively. So it's really important to detect colorectal cancer at an early stage, and so it's so important that, for example, in the United States, they start screening for colorectal cancer at 45. It was 50 years of age, now it's 45, and so this basically shifted the number of colonoscopy in a year in the United States from 15 million to 22 million. And so there is no capacity to get 22 million colonoscopy a year in the US, and so maybe robotics can help there. Also because screening is typically, so you screen healthy population, typically healthy population, and so about 90–95% of those procedures are negative. So it's just going inside, look if there is cancer, and in 95% of cases is nothing else to do. So this can really be automated using robots. So what is the way to screen for colorectal cancer? In many countries is colonoscopy. So colonoscopy entails the introduction of a 1.5 meter long tube from the anus to navigate the colon up to the cecum, up to this part here. So this instrument has a camera at the tip, a light to illuminate the lumen, the irrigation nozzle to clean the camera, but also to inflate the lumen and create space for the camera to see. It also has cable that run through the length of the device to articulate the tip in 2 degrees of freedom, left, right, up, and down, and those cables are connected to those 2 knobs that are moved and controlled by the operator with the thumb. It also has an instrument channel that is used for instrument to go through and remove polyps and interact with the tissue, basically. So what are the problems of this procedure? This procedure is extremely painful, and the reason is that when the endoscope goes inside the body, since the anatomy is not straight, but is very convoluted, when it gets to a bend, they need to push, stretch the tissue to advance. So there is no way, no alternative way for this to proceed at the moment, because it's just a tube being pushed from the outside, and it's stiffer than the surrounding tissue. For this reason, it stresses the tissues. So this tissue stress creates pain, so much so that most of colonoscopies, especially in the US, are done under full anesthesia. So not everybody can get fully sedated, especially if people have cardiovascular issues. And also it's very expensive to have anesthesia, anesthesiologist in the room, and so on. So it would be nice to have a painless procedure for colonoscopy. Also, colonoscopy is very difficult to perform for the operator. It requires a long training, and also there are issues related to this instrument that after 10 years of practice, the gastroenterologist can get issues at the wrist. And also the instrument itself is very expensive. So it's about, let's say, $50,000, $60,000. So it needs to be reused. And so this limits colonoscopy only to measure hospital or endoscopy center where the endoscopes can be cleaned and reprocessed. So it would be ideal, again, to have something that is painless, driven easily like a robot or like a car in a video game, something like that, and also something cheap that can be made disposable so that colonoscopy can go out in the field or closer to the patients rather than just in major hospital and centers. So robotics have been working in this field for a while, and for example, in this review paper, there are a lot of devices for this type of procedure, and only one of those is FDA approved and it's on the market. And so this device is from a spin-out company of Scuola Superiore Sant'Anna. It's bio-inspired because it works as an inchworm with inchworm locomotion. So it has 2 clampers, one at the back, one at the front, and the body can elongate. And so it clamps at the back, elongate the center, body clamps at the front, release at the back, and retract the body. So it's also a soft robot, so it's very much in line with what we have been talking these days. As it happens, I did my master thesis on this device, and now, yeah, it's being in use. So since I passed 45 years of age, and I'm interested in robotic colonoscopy, I decided to get one of these procedures done on myself. And so here, this guy is one of the co-founders of the company, who now works for my company. So we poached him from the company, from the competition. And about 1 year ago, I went to a hospital in Pisa and got this procedure done. So you see me before the procedure. So this is the inside of myself. So it looks like very clean colon. I had no issues, so in that regard it went well. But it was so slow, extremely slow. So the robot took 57 minutes to get to the end. And consider that a normal colonoscopy takes 5 minutes to reach the cecum. The robot broke inside myself. So at some point, the back clamper stopped working, and so the robotic navigation was not possible to run anymore, and so they had just to push it like a normal endoscope. And so it was not pleasant procedure. And so that confirmed that there is still a lot of space in this area to improve. And so how to improve on this? Certainly we want something faster. And so the inspiration we got probably is something that many in this room, certainly some in this room has get inspired as well, came from this.
Using this magneto, I will now guide the keys up the thorax and out via the frontal face hole. That's the storage locker. A boat. The other boat.
So basically the idea is to use a magnet to navigate something inside the body. And so for us, this something is a soft, flexible endoscope with a permanent magnet at the tip. And from the outside, we have a robotic arm with a permanent magnet, a big permanent magnet. So the other component of this device are the same as a flexible endoscope. So we have an instrument channel, camera, nozzle, light. And so we are able to do the same procedure that conventional colonoscopy can do. In particular, we have an instrument channel, so we can pass an instrument. But the point that we don't need to push anymore because we are pulling with magnetic fields. And we don't need cables to steer the tip because we can steer with magnetic fields, make the body of the device extremely flexible. And so you see it compared to a pediatric colonoscope is definitely a different story. We also, so with that we believe this can be painless. It also can be intuitive because we have a joystick to control the device motion looking at the camera. And also this in itself is a low-cost device, so the bill of material is just $10, so we can definitely make it disposable. And so I was also talking about time during the first slide of my talk. So this was first published by us in 2012 when I was still in Paolo Dario's lab at Scuola Superiore Sant'Anna. I was assistant professor, but working with Arianna Menciassi and Paolo Dario at the time. Now, about more than 10 years later, this is how we look like. So this is my company, Atlas Endoscopy, and this is the robotic arm. We use a KUKA medical robot. This is the external magnet, and this is the probe. So again, extremely flexible, same component, more or less, and we have a joystick. So with one hand, the joystick, we use the joystick to orient the tip and move forward and backward, and with the other hand, the operator feed the tether or pull it for when you want to come back. So the key point of this platform that makes it work is localization. So when we talk about magnetic manipulation of medical devices inside the body, I always stress that localization is crucial for closed-loop control and intelligent magnetic manipulation. And so the core IP that we have in our company is real-time localization that I developed when I was at Vanderbilt University. And it basically uses magnetic field sensor and inertial sensor at the tip of the endoscope. And the magnetic field sensor is measuring the field generated by the external magnet at the tip of the endoscope. Then with the inclinometer, we rotate the vector in the frame of the external magnet, and we do a search in a pre-calculated magnetic field map to get the pose of the tip of the endoscope. We also have a coil here. This coil is just for localization. And basically, since we are using a permanent magnet which is axially magnetized north-south, we have a singularity plane in the middle. And so we need to create a magnetic field which is different in that singularity plane to localize the tip. And so this coil is creating this non-homogeneous field in the singularity plane of the permanent magnet. And so once we have real-time localization, then we can explore different level of computer assistance from basic teleoperation, intelligent teleoperation, I would say, in a sense that we look at the image coming from the camera, and then with the joystick, we do left, right, up, and down in the frame of the camera. And then the system localize the tip of the endoscope and move the external magnet accordingly. And so this is basic robotic assistance. We also have lumen detection algorithm, but in this case we use it to inform the operator in case we lose the view of the lumen. Like we have an arrow that tells the user that where the lumen is. We can use localization together with image analysis to recreate the colon in 3D. This is quite a cool addition in our platform. So for each patient, we can recreate a map of the colon in real time that can tell the operator if there are blind spots that were not visualized. And so we can basically guarantee at the end that the colonoscopy has visualized everywhere in the colon so that no polyp, no cancer is left behind. And so you see this is a map generated at the end of a colonoscopy. If there are some spots like this that has not been reconstructed, then it means the operator has to go there and check again. And we can also, of course, mark where a polyp has been removed, where a cancer was for future colonoscopies. We also work on task automation. So in this case, we have automated retroflexion, which is from looking forward to look back. So our system is flexible enough that can retroflect everywhere, differently from a conventional colonoscope. And basically, we push a button, the system localizes the tip of the endoscope and retroflects. We have a version of our endoscope with a lateral ultrasound array. So basically, we can sweep around the lumen. So in this case, we have some copper wires that we are visualizing with the ultrasound array at the side. And so we did some animal trials where we injected some liquid solution, saline solution, and then we did a sweep, and we were able to reconstruct the pocket created by saline solution under the colon mucosa, up to autonomous colonoscopy. So this is like self-driving inside the colon of a pig. We have, again, lumen detection that tell us where the center of the lumen is, and then we go in that direction. And this is like the reconstructed trajectory after, after the experiment. Then, eventually, first-in-human trials. So we did first-in-human at Vanderbilt University in November 23. So it's about 2.5 years ago. That was really like, for me, I was there in the room just taking pictures, very happy. I didn't contribute. The team contributed and did the full procedure. I was just there taking pictures, really happy to see what we started as an idea, bench trial, animal trial, and finally human trials. So the human trials, we had 5 patients undergoing screening colonoscopy. They first got conventional colonoscopy under full anesthesia. After they recovered, they were basically back awake, we started with robotic colonoscopy. And so they were interacting with us, talking with us, and that was really convenient because at some point we need to turn them, and they basically turned by themselves. No adverse event, which was good. And all of the patients well tolerated the procedure. We did questionnaire at the end. They were all, they didn't feel anything really. And so this is, of course, this was the goal of first-in-human was to assess safety, so to verify safety, which was verified. Now, to do further studies, we need more patients. And so we have, with the company now, we are ready to start larger trials. So earlier this year, we got the 6601 certification for, this is like electromagnetic safety and compatibility. And again, we got it January this year, but it wasn't easy. So we were ready to do that 1 year ago. No, 6 months before, we failed it because one of the engineers didn't connect the probe to ground, and we failed that test. Then we had 6 months of redesigning, went back and got certified. We got certified for biocompatibility. That also was another 6 months of pain. And we also got certified. This is the certification to produce the device in-house in our company. And this this arrived like during 1 month ago, and this arrived at the beginning of July. So now our platform is at the moment is in Pisa at the University Hospital, where I got my colonoscopy and where they did the human trials that allowed the company of the inchworm to get FDA approval. And so we are starting now in August, and we aim to do 20 patients, compare with colonoscopy. So each patient will get colonoscopy and a robotic colonoscopy in a randomized order with a randomized operator. So we have 2 endoscopists, and they will be randomized on the type of procedure. This should bring us enough data to file for FDA approval by the end of the year, fingers crossed if all goes well. So yeah, I mean, and that concludes my first part, and then I'll be happy to chat with you if you want more knowledge about the pain of running a company. But also like the reward, it's a rewarding experience as well. Now, back to the scientific part. So the second part of my talk is about magnetic tentacle robots. So this is very much inspired by Metin's research that he showed yesterday, the one where the soft material is magnetized with a magnetic profile. So that work came out in 2018 and got me inspired to write my Consolidator Award, where we basically wanted to have full control of the shape of the catheter. So rather than controlling the tip of an endoscope with a simple permanent magnet outside, we want now to control the full shape, and we want also to shrink down the scale. And so very basic fabrication techniques, silicone with magnetic particles, and then magnetize in different shapes depending on the task we want to do. So for example, in this case, we want to get this target, avoiding those 2 obstacles. So we have a specific magnetic profile, and then we create a magnetic field with 2 permanent magnets that can accomplish this task. Of course, we can do this with coils. We like to use permanent magnets because they are easier to get to the operating room. They are smaller in footprint. But of course, we lose 1 degree of freedom, which is the intensity of the magnetic field. So we have a paper that shows that with 2 permanent magnets, we can control up to 8 magnetic degrees of freedom. So potential applications, first application we used this was for bronchoscopy. So bronchoscopy is similar to colonoscopy in a sense that there is still a flexible endoscope that goes inside the bronchial tree up to the point where the tumor is, in case of lung tumor, of course. So this instrument is okay if the tumor is in the first branches of the bronchial tree, but then at some point, if the tumor is peripheral, the flexible endoscope cannot progress up after the 3rd branching due to the diameter. And so from that point, typically the surgeon introduces a catheter which has only 1 degree of freedom and is visualized under X-ray. And this procedure is extremely difficult. And so what has been done in this field was several companies, including Intuitive and Johnson & Johnson, developed a robotic endoscope for bronchoscopy, so a robotic bronchoscope, but no one really did a robotic catheter that goes out from the endoscope. So we tried to do just that. So a robotic catheter that coming out from a bronchoscope, whether manual or robotic, it's okay, but then we robotize the catheter. So in this case, we have a magnetic tentacle, 2.4 millimeter in diameter, with fiber Bragg grating to get shape in real time and try to do closed loop control, and also laser fiber to deliver energy. And so we did a lot of bench trial, but then we went to cadavers. So in Leeds, we have a very nice facility with TL embalmed cadavers, so soft tissue cadaver. And so that's a very good model, especially in this case for bronchoscopy. And so we had X-ray just to take pictures, and this was a pre-planned navigation, pre-planned trajectory to different peripheral area of the lungs. So we were able to, and we compare with the manual catheter. And so very often we were able to reach deeper, and also we did not deform the anatomy as the manual catheter. Because again, the manual catheter is way stiffer and needs to be pushed, while in this case, we are basically navigating a magnetic tentacle with full control of the shape. Another procedure we are interested in is pancreatic intubation. So pancreatic cancer is not very prevalent, but is deadly, really deadly. So the 5-year survival rate is marginal, it's really terrible. And so how to get to the pancreas to deliver drug, typically with another flexible endoscope, this time a gastroduodenoscope. And so basically we get through the esophagus, stomach, and first part of the intestine. Once we get there, from the instrument channel, a catheter or whatever else is delivered to the papilla, which is this little hole, and then it goes to the pancreatic or the bile duct. And so again, we want to robotize that last part. So we develop magnetic tentacles with different magnetization to either go to the bile duct or to the pancreatic duct. And then this was 2022. And then more recently, this is still unpublished. It's on the second round of review at the moment. This is a 1.5 millimeter diameter tentacle with a balloon to stabilize the head. We have a camera and a gripper. And in this case, we were also interested in autonomous intubation in the papilla. So this is manual teleoperation, looking at the camera, feed, and trying to control the tentacle to go inside here. And in this case, is automated using visual clues. And so we did this in pigs. And so you see, this is the view of the endoscope. This is the view from the tentacle itself once we are in the papilla. And we compared teleoperation with autonomous insertion. And you see, this is the trajectory of the tentacle. And you see how rougher it is if compared to autonomous insertion. And autonomous insertion went way better. So it's something that we believe can contribute the automated and guided assisted navigation to get pancreatic intubation. And then last part of my talk, this is something very new. We started from a collaboration with KAIST in Korea and University of California, San Diego. And we got inspired, of course, by Vine robots. We have seen this yesterday, so I'm not going to explain it again. But the beauty of a Vine robot inside the body is that we don't have friction with the external lumen. So it's something that grows from inside, and we don't have to work against the lumen wall. And so this is the first our first approach to magnetic Vine robot, again, collaboration with the G1 Ryu group from KAIST. We basically got our magnetic endoscope, and instead of pulling with magnetic fields, we were advancing thanks to a version of the Vine robot. And then we were using magnetic field for orienting the tip, as well as for retraction. So we showed that with holding the tip of the endoscope in a proper way, retraction of the Vine robot works effectively. And in this case, we had real-time localization, which is, again, crucial for intelligent robotic manipulation, magnetic manipulation. And you see, we are basically advancing a convoluted layout with the version, and then we steer the tip. So where this can be important, this is important if we go to the small bowel. Because for the colon, we can still pull the tip of the magnetic endoscope with gradients, so with magnetic force. But after the length of the colon, the friction of the tether becomes too much, and so magnetic traction doesn't really work anymore. So it's good to have a different way to move forward. Then I was mentioning collaboration with Tanya Morimoto, University of California, San Diego. So we tried now to make them smaller. And so first attempt was to make a magnetic skin. So in this case, it's silicone with magnetic particles. And in this case, it worked quite well. so the steering works, but the problem is that the magnetic volume is so low that we have to be very close with our permanent magnet to guide, to steer. And so we did move to a different approach where instead of inflating the averting robot with gas, we use magnetic fluid. And so by filling the robot with magnetic fluid, we have way more magnetic volume, and so we can move and control the direction of growth from farther away with our magnet. In this case, we are again working on bronchoscopy, and this is a magnetic vine robot which at the tip has a camera and also an instrument channel to get biopsy of a sample. So you'll see in a second that we get a biopsy with an instrument. And so, and this is again an ongoing collaboration we have with Tanya Morimoto, and something that just started very recently, and this is supported by ARIA, which is a new funding agency in the United Kingdom. Here the idea is to deploy neurotechnologies without craniotomy. So if we want to implant, to have a neural implant, like for epilepsy or for whatever reason, instead of having to open the skull and implant the electrodes, we want to go from the spine with a lumbar puncture, which is a very easy procedure to do. So it's typically outpatient procedure. And then from there, we navigate a vine robot inside the spine and manipulate it with external magnetic fields. So this is the vine robot that we have developed. And this is a cadaver trial. And so this is the image from the vine robot inside the spine of the cadaver. So the this channel in the spine, the CSF space, the cerebrospinal fluid channel, is quite clear, and it's a very nice way to navigate inside the body. So that was a result that we recently got that surprises even the neurosurgeon working with us. And yeah, you see here, this is X-ray. You see the tip of our vine robot navigating the spine. Okay, with this, I'll basically conclude again by saying that if you really want to get your technology in the field of medical robotics to the patient, it takes time. Get some white hair in the process, but it's really rewarding. So I would like to acknowledge my team and all the funding agencies that supported my work, and also invite you all in Leeds for CRAS, which is a conference in surgical robotics that I am organizing in September. So if you want to visit and see what we are doing, also like join this conference, you'll be very welcome in Leeds. Thank you for your attention. Thank you.